Okay, so we're going to solve some systems of equations using the elimination method. And then we're going to verify that, justify that graphically. Okay, so we're really going to be using two of the three methods that we've been studying. So to start with, for elimination, remember I need to force one set of variables to be opposites. So either the x's or the y's. It's completely your choice, my choice. We don't have to do them the same way. Now, since this has a decimal in it, you might be tempted to try to get rid of that, and that's fine. But just know that there's also a decimal in this equation, so you're probably not going to get all the decimals out of the problem. Okay. So I feel like it would actually be easier for me if I just multiplied this bottom equation by -2. That would turn it into -2x, -4y, and -17. And then I can add the first equation, the one I did not alter, to the new one I just made with blue. Okay, so I add those together, 2x and -2x. That variable's eliminated. That was my intention. 1/2 y minus 4y would be -3.5y. And then 3 and -17 is -14. Well, to solve that one-step equation, if I divide both sides by -3.5, then y is equal to positive. Negative over negative is a positive 4. Okay. Now, to solve for the other half of the point, to solve for the x, I need to substitute that 4 back into one of the equations. It doesn't matter which one. It is completely up to me. So I'm going to put it in this first one. So 2x plus 1/2 times 4 is equal to 3. Well, that becomes 2x plus half of 4 is 2 equals 3. Subtract 2. 2x is equal to 1. Divide both sides by 2. X equals 1/2. So my solution is the point 1/2, or 0.5, 4. Now, to verify that graphically, what I'm going to do is graph each of these equations, each of these lines separately, and look to see that my intersection point looks like it's 1/2, 4. Now, anytime you're graphing, there's a possibility that you don't graph totally accurately. It might not look perfect, and that's why that's not such a reliable method. But it should look at least close to 1/2, 4. So I recopied my two equations down here. I want to work with the original equations, not the one that I changed or the one that I made. And since they're both in standard form, the simplest way to graph them is to find their intercepts. Okay? So I will find the x-intercept and the y-intercept for each of these equations. So remember, the x-intercept is when y equals 0. So if you substitute 0 for this y, 1/2 times 0 is 0, that whole term is just gone. Okay? So momentarily, just pretend that's not there. Guess when we did this previously, I pulled out a little square to cover it up. Of course, that's not covering, still able to see it, but pretend that's not there. 2x equals 3. Well, if I divide both sides by 2, that means my x-intercept is 1.5. For the y-intercept, I would do that with x. So pretend the x's are gone. So I have 1/2 y equals 3. Divide both sides by 1/2, and that's not 1.5. 3 divided by 1/2 is 6. Okay. Let's go to our other equation. Oh, having trouble dragging my little square. For the x-intercept, I cancel the y's. X is equal to 8.5. And for the y-intercept, ignore the x's. 2y equals 8.5. So 8.5 divided by 2 is 4 1/4, 4.25. Okay. So that first equation, I'll graph this one in red. The x-intercept is 1.5. The y-intercept is 6. Those 2 points should provide enough that I can graph my line. Now, because I do want to make sure I can see the intersection point, I probably want to extend my lines as far as I can, right through the graph. All right, I'll do the next one in green so we can tell them apart. The x-intercept is 8.5, 8.5, and the y-intercept is 4 1/4. So I've got to estimate that. Here's 5, here's 4, so about 1/4 of the way to 5. Whoops. I just put that in the wrong axis. I'm sorry. The y-intercept is 4 1/4. Excuse me. So there. And then let's graph that line. So does it look as if those two lines intersect at 1/2, 4? 1/2, 4. Yes, that is quite possible to see that point as 1/2, 4. Number 2 is I look to try to eliminate one of the variables. I'm actually going to do this one by a harder method than I would normally, but I want you to see it happen. So normally I would say I can make these x's opposites by just multiplying the bottom equation by -3, and I would only have to change that one equation. I want to make sure you are aware of how to do this, though. I can make the 2 and the 5 opposites by asking myself, what is the least common multiple of both 5 and 2? What do 5 and 2 both go into? And the answer to that would be 10. So if I want to try to change these into having coefficients of 10 and -10, I can multiply the top by, say, 2 and the bottom equation by -5. So that top equation turns into 6x plus 10y equals -2. And the bottom one becomes -5x minus 10y equals +5. And those will be the two equations that I add. 6x and -5x makes 1x. 10y and -10y were eliminated, equal to -2 plus 5 is 3. And just lucky for me, I don't even have to solve anything. I have one of my variables, x is 3. And then I would plug that back into either of the other equations to solve for y. I'm going to plug it in right here. So 3 plus 2y is equal to -1. To solve that, subtract 3 on both sides so that 2y is equal to -4. Divide both sides by 2, y is equal to -2. So my solution is 3, -2. And now, to graph my two equations, remember I want to go back to the originals. So one of them is 3x plus 5y equals -1. It's in standard form, so I will graph it by finding the x and y intercepts. The second equation is x plus 2y equals -1, also standard form. So graph it by locating the intercepts. So if I grab another little box here and say, all right, to find the x-intercept, I want to, I'm having trouble with grabbing the box again. To find the x-intercept, I'm subbing 0 for y, so this 5y term is gone. Then the x-intercept is -1 divided by 3, -1/3. For the y-intercept, I have sub 0 for x, so the 3x is all gone. 5y equals negative 1, so that y-intercept is negative 1/5. So that line has an x-intercept of negative 1/3 and a y-intercept of negative 1/5. Now, those points are so close together that that line is probably not going to look great when I have graphed it. They're probably a bit too close together to be of much use, but we'll put her up there and see what happens. If things don't look good, I can always go find some more points to graph with. So in the blue line here, for my x-intercept, I'm ignoring the y term, so x is equal to negative 1. And for the y-intercept, I'm ignoring the x's and solving 2y equals negative 1, which gives me a y-intercept of negative 1/2. Again, these are also very, very close together. The x-intercept negative 1, the y-intercept negative 1/2. So when I graph that blue line, also probably not going to be the most accurate of lines. So, yes, I was afraid of that. What my graph shows, well, it doesn't show what I wanted it to. It does not look like those two lines are intersecting at 3, negative 2. Now, my blue line does hit the point 3, negative 2, but the red one does not. It's hitting at 3, negative 3. Now, I'm sure that is just because my two red points were so close together that I did not get an accurate line. So what I would do, if my picture doesn't look the way I want it to, is go back to this red equation and actually try substituting the 3, the x value, into the equation and make sure that I do get negative 2. And if I do, then I can go ahead and add that as one of the points on that red graph and change my line. So if I substitute 3 for x, I guess I don't even have to solve for y. I can go ahead and substitute negative 2 for y and just make sure it's correct. 3 times 3 is 9, plus 5 times negative 2 is negative 10. And 9 plus negative 10 does equal negative 1. So that lets me know 3, negative 2 is a point for the red line. So if I were to remove the first attempt, again, it wasn't that either of those first 2 points were incorrect. They were just estimates because they were fractions, and they were so close together that I couldn't tell exactly how or where to draw my line. So this is a much more accurate representation of the graph. Okay, number 3. And yes, we are going to have a fraction involved. If we're lucky, we'll be able to multiply by something to make it go away. But if we're not so lucky, we can live with that. We'll deal with it. So to make one set of variables opposites, again, 2 and 5, 2 doesn't go into 5, 5 doesn't go into 2. So I would have to change both equations to make the y's opposites. That's what I did in the last problem. This time I'll just go with whatever looks simplest. And that is, if I multiply this bottom equation by negative 3, it's actually going to make opposites for x, which is my intention. And just out of pure luck, it's going to get this fraction out of there also. So negative 3 times x is negative 3x. Negative 3 times 2y is negative 6y. Negative 3 times negative 4/3. Well, negative times negative is positive. And 3 times 4/3 is positive 4. So I will add in the top equation and the new blue one here I just made. When I add those, 3x and negative 3x is eliminated. 5y and negative 6y is negative 1y. And negative 3 and 4 is 1. Divide both sides by negative 1. Y is equal to negative 1. Substitute that value into any of the equations. I'll just choose this first one for no particular reason. 3x plus 5 times negative 1 equals negative 3. 5 times negative 1 is negative 5. Add 5 to both sides. So 3x is equal to 2. Divide both sides by 3. X is equal to 2/3. So the solution to this system is 2/3, negative 1. So again, we need to graph the two original equations. So I will make this first one, 3x plus 5y equals negative 3, an orange equation. It is in standard form, so I will graph it by finding the intercepts. I'll make the other one purple for contrast, so x plus 2y equals negative 4/3, also standard form. So let's identify the two intercepts. So the orange guy here. For x-intercept, I am ignoring the y values. So if that term 5y is gone, I'm left with 3x equals negative 3. Divide both sides by 3, x-intercept is negative 1. For the y-intercept, I'm ignoring the x terms. So I have 5y equals negative 3. Solving that, I get negative 3 over 5. Well, let's go ahead and graph that one, I guess. X-intercept is negative 1. Y-intercept is negative 3/5. Oh, geez. Here again, we have one where our 2 points we found are so close together that we're going to have a hard time making an accurate graph. But we can put it on there for now, reserving the right to make that better if need be. All right, the purple equation here, my x-intercept, I ignore the y's. So x is equal to negative 4/3, or negative 1 1/3, don't round that. The y-intercept, I ignore the x's. So that gives me 2y equals negative 4/3. When I divide both sides by 2, this is really negative 4/3 divided by 2 over 1, which means I really do negative 4/3 times 1/2. So negative 4/6. That reduces to negative 2/3. Once again, do not round. So my two intercepts, x-intercept, negative 1 1/3. Y-intercept, negative 2/3. Once again, very, very close together, very hard to graph accurately. But this time, I feel like I did a little better job of getting it in the right place. Because those two lines do look like they might be crossing at 2/3, negative 1. 2/3, negative 1. We're pretty close anyway. And last one, we actually have a scenario word problem here. So we're going to have to make our own equations and then go through all the steps. So Raekwon has a coin collection consisting of nickels and dimes. He has 28 coins, that's the total, worth $2.25. So how many of each coin? That means I have two unknowns. I have to write two let statements for X and Y. My two unknowns are number of nickels and number of dimes. And I need both because how many of each coin? So what are my two equations going to represent? Well, the information up here is about number of coins, and the other one is about the value of the coins. So 2 equations, one about number, one about value. So my equation regarding number would be how many nickels I have, that's X, added to the number of dimes I have, Y, must equal the total coins, 28. Now the equation representing their value, I need to know, it's not written in the problem, but hopefully you know that a nickel is worth 5 cents and a dime is worth 10 cents. So all of those X nickels are worth 0.05 X, and all of those Y dimes are worth 0.10 Y, and the value of nickels and the value of dimes combined is $2.25. Now, in order to get opposites here, I'm either going to have to turn one equation into decimal numbers or turn the other one into integers. I feel like you would probably rather work with integers. So if we ask ourselves, like for example here, if we decide we're going to make the y's be opposite, this is 1y. To make this be negative 1y, I have to multiply it by negative 10. Right? It takes 10 dimes to make one whole dollar, but I want it negative. So multiply by negative 10. Right? So this second equation, when I multiply by 10, it moves a decimal one place. That becomes negative 0.5x minus 1y equals negative 2250. Now I add the first and the bottom equations. So 1x plus negative a half x is a half x. 1y minus 1y is eliminated, just like we intended. And 28 and negative 2250 gives me 550. So my one-step equation to solve, I divide by 1/2. So x is equal to 11. That's one of my variables. To find the other one, I need to substitute back into one of the equations. The simplest one would be this x plus y equals 28, because it just gives me 11 plus some number equals 28. Well, subtract 11 from both sides, y must be 17. So that means I have, since x was 11, I have 11 nickels, and y is 17, I have 17 dimes. Or Raekwon has 11 nickels, 17 dimes. The point on the graph would be represented 11, 17. So how are we going to graph this one? Well, this one doesn't have a scale, so let's find all of our intercepts for both equations first, so we know what kind of scale to choose here. So our x and y intercepts for the first equation, x plus y equals 28, when I ignore the y term, x is equal to 28. When I ignore the x term, y is equal to 28. So both intercepts are 28 for that equation. Now, for the other one, I'll make this one blue. If I ignore the y term to find the x-intercept, I'm left with this, 0.05x equals 2.25. Well, when I divide both sides by 0.05, that is 45. When I reverse that and I get rid of the x term and just solve 10 cents y equals 225, divide both sides by 0.10, y is equal to 22.5. So it looks like I need to make it to 45 on my axes. And since I have 2, 4, 6, 10 boxes, I could count by 4.5. I wouldn't get into those decimals, so I'm going to make my scale 5s. Okay, so this would be, oops, let's pick another color for that. 5, 10, 15, 20. Okay, there we are. So my red equation over here, the x plus y equals 28, had both intercepts of 28. Both x and y intercepts were 28. So that's much better looking graph than the last two, where our x and y intercepts were so very close together. Let me extend that. And then our blue intercepts, we have one at 45 and one at 22.5. So again, those are more spread out, give me a much more accurate line. So could those possibly be intersecting at the point 11, 17? And that wouldn't have been my guess, but sure, we can call that 11, 17.